So, all right. Welcome to Quantum Crash Course. This is part two of the quantum circuit practice problems. So, please fill out this attendance and Boiler Link. If you've already done the attendance last week, don't worry about it, but go to the Boiler Link page and request to join the QSO group, because this is what we're going to use as this qualifies you as a member of QSO officially in terms of like elections, which are coming up soon. So yeah, while you're doing that, I'll just talk about this, which isn't a lot of detail-oriented stuff. So we're going to do problems related to linear algebra, Bra-Ket notation, and some of these will use, we're going to use quantum gates, and this will use concepts of superposition and entanglement. The goal is to understand how to use the Bra-Ket notation well, or you could use the linear algebra version, and then you can use the block sphere with that to solve quantum circuits. So we're gonna just breeze through this, I think. I'll probably write some of this stuff up on the blackboard. You can also feel free to take a picture of it if you want to refer to it yourself. So Bra-Ket notation and vector representation. So the zero ket is represented as a vector in linear algebra with 1, 0. And then the 1 ket is 0, 1, right? And you can use linear algebra. You can also use purely Bra-Ket notation to solve these problems. I'll just flash it. So these are the problems. These are quantum circuits. So yes. So now we have tensor product. No, I'm not going to get into that. So let's just start with that. So Bra-Ket notation up here. On the very top, we have the ket of a quantum state, right? We have this variable, just some quantum state psi. And then we have 0 ket and 1 ket, which are kind of your basis vectors, if you know linear algebra. And you have coefficients a and b in front of them. And then we have the condition that the magnitude of a squared plus the magnitude of b squared has to equal 1. And that's just a normalization requirement. Then we have this bra version of the same thing, and that's all there is to it. We're just going to use the ket notation. That's all you need today. And then tensor product, I'll highlight that. So that's just to represent when you have a quantum circuit, you have the multiple lines, right? And then each line, you can say that this is the top line and this is the second line. If they're both in the 0 state, this is how you kind of join them together into one notation. And then we have Pauli matrices, which are basically gates, which we can go into. So let's go through the lightning round. All right, what does Pauli X do with the block sphere in terms of the block sphere? What does it do to your vector? 180 about what axis? X. Nice. And then Y. What do we do? Pauli Y. 180 degrees, but around the y-axis. Same for z. Hadamard, what does that do? Puts it on the equator. So if you have a quantum state that's in the 0 or the 1 state, up or down, and you apply Hadamard to it, it's going to go to the equator. Controlled knot, controlled z is kind of good to know. Swap and Toffoli. Who can tell me what the controlled knot does? Like in terms of, don't worry about the block sphere anymore, but in terms of like a quantum circuit representation.
The
Ben,
controller is on and the receiver changes its state,
how does it change it?
like opposite of what it was before, I think.
Yes, so the controller is the top or the bottom here?
Top.
Top. So that the little black dot is your control qubit. And then the bottom, whatever's here is your target. We can look at the controlled Z, and it's the same concept. The little black dot is your control, and the Z is your target. And then whatever is pictured here at your target, that's what you're going to do onto that qubit if your control is 1. So here, this is basically another way of showing the X, as you can see up there, the poly X gate. So what you're going to do is if you have a 0 in this qubit and you encounter the poly X, it'll become a 1. But it's only if your control is activated. Same idea here, except you're just going around the Z-axis. Swap, you're just swapping two qubit states. And then Toffoli is the same idea as this controlled knot, except now you need both of these qubits to be 1 for this to be activated. So if you only have one of the two controls on as a 1, nothing happens. Yeah.
What did the matrices represent, especially like the larger matrices, like the Foley, stuff like that?
So that's more like the linear algebra approach, right? I guess what do you mean? I don't know if there's I'm struggling to understand what your question is, I guess.
So what are you supposed to do, like look at matrices?
Okay. Yeah, so right. So for the 2 by 2 matrices, I think it's a little bit simpler to understand, right? Because you have states of 0 and 1, which are represented as a vector that's 2 by 1. So it's compatible with these matrices. So what I was saying is that when you have a matrix, what, 0, 1, 1, 0, I think that's a Z, right? And you're acting on state 0. So this is the same thing as saying Z gate acting on state 0. But how do you do like a C naught on like state 0? Is that your question? I think that's kind of what you're getting at. So I guess, but C naught is a 2-qubit gate. 2-qubit gate. So you're gonna have to have like two things, two states, 2 qubits. So I think to answer your question in a succinct way, uh, you can take this vector for 1 qubit and you can do the tensor product with another qubit to make a higher dimensional vector, which would be compatible with this C naught, which has, whatever, 4 by 4. Does that kind of make sense?
So basically, depending on how many entries or like dimensions are in your matrix, you have to have like a matching state vector.
Right. So,
in order to so like poly X, let's say you have a qubit in 0 state, which is a 1, 0 column vector, then the multiplication operation between that state vector and the gate matrix, like that is allowed. If it were like in the case of the CX gate, if you have just the 1, 0, so just one singular 0 state qubit, then you literally cannot do the matrix multiplication operation.
Oh, okay. So yeah.
yeah, so it's a linear algebra rule. If you have a 2 by 2 matrix and a 2 by 1 vector, they're compatible if these two numbers are the same. So you can't have 0, 1, 1, 0, and like 4 by 1. So now you got 2 by 2, 4 by 1. That doesn't work. Okay, great question. With that, let's get into it. Nah, I'm not gonna do that. All right. So I don't know. We're gonna move on from this. So we're running out of time. So basically, I'm just gonna try to go into an overview of the last part that I was trying to get into, which is where you sketch the probability distribution of the states that you just got. You have so if you look over at the board, see that psi 3 on the far right, where you have like 4 different terms. That's like an example of what your final answer might be. That's not the right answer for number one, but that's an intermediate answer. So that's that's an example of a quantum state you could have, and you could sketch out a little graph like this where you have probability of each state. So I'll just skip ahead and I'll show you that for this one, for number one, this was your if this was your final answer. So the probability distribution is equal parts all 4 of these combined states. So you have oh, did I make an error? Maybe I did. So this one is 0, 1, 1, 0. This is 0, 1, 1, 1. Maybe I screwed up. I don't know, but okay. Moving on. Wait, oh, it's just, is it reverse? Okay, it's reverse. Does that make sense? So no, I'm saying that right here I have 0, 1, 0, 0, but here they're like reverse. They have
Yeah.
0, 0, 1, 0.
That's
Okay,
how-
that's how Qiskit does it. So they say that when you write um, when you have 4 qubits, 1, 2, 3, 4, then you write them as psi 4, psi 3, psi 2, psi 1. Whereas we did the opposite today. We were top down, right? So that's a little bit confusing, but um, I think that proves that this is right. So the idea is just you have all these terms that are when they're in this fully simplified form, then it's really easy to make these distributions. But if you're not in a simplified form, um, like you still have some of these like not fully distributed, then it's not so easy. So that's kind of the point. Any questions on this? Okay. I think that's all. And I think everyone already did this stuff. So um yeah, sorry I couldn't let you guys do this on your own, but oh, and just another thing I'd like to note was so here we have a very simple circuit, just 1 qubit, and then here there's usually like a double line that you can't see because of the projector. This is a classical bit. This one is a quantum bit. This is a classical bit. So what happens with a quantum state, you can measure it, and that's how you get a probability distribution when you measure it in an experiment. And then once you've measured it, there's nothing more quantum about it. It's no longer quantum, it's classical. So then you take it and you put it on this classical bit.
And you have to do it like a lot of times is the idea.
Right. It's just like flipping a coin. Um, you can't just do one flip and be like, oh, it's always going to be heads, you know? You need to do it, hundreds of times, thousands of times, and then you'll see that there's a distribution that's 50 and 50 for heads and tails. So it's the exact same idea here. Because you can think of the coin when it's flipping in the air is in a quantum state. And then when it lands, classical. Does that make sense? That's how you can think of it.
So what's up with the two measurement?
You're talking about this? Yeah, so you can measure, I mean, individual qubits. hmm So yeah, you do measurement on each qubit. If you get into, I think what is it, like Shor's algorithm. So you can, this is like really complicated quantum circuits. So you can do oh gosh, I'm rusty on this, but anyways, you'll have something called an ancillary qubit, which if you know anything about classical, if you have classical error correction, you'll have some ancillary bit, which is basically a bit that tells you if there's been an error that's happened. In quantum error correction, you can use Shor's algorithm and Grover's algorithm, maybe. I don't remember the details. And these algorithms you can put into actual hardware, quantum circuits, and you'll have an ancillary qubit, which you can measure, and it'll always be one if there was an error detected, and it'll always be zero if there wasn't. So my point is, you don't always have to measure every single qubit you have classically.
So the kind of- so it's like- stuff. So,
Yeah, it's kind of it's a gauge. Yeah. I'm kind of rusty on that. It's been a while. It's been a full year since I took that class, but yeah.